Okay, so thanks very much for this nice invitation. Actually, this is the first time when I'm going to give a Zoom conference talk, so I'm not very experienced with that. So I will talk about the work which actually we have done together with Horton, Yau and M with Salmhofer several years ago. And there is no really new result in that, but I thought that this is a result, or it's an idea sequence of ideas which would actually fit very well to this conference. And I guess probably you would be more interested in this result than my more recent work, but I would be happy to talk about other things as well. Anyway, so I will, at the beginning, I will give you a quick overview of various models which lead to the Brownian motion. Some of these things are probably well known, so I'll be very fast at the beginning, and then when I will come to the actual quantum Brownian motion, I will slow down. So don't get scared if the first few pages will be very quick. So I will talk a little bit about overview, first introduce the random Schrodinger operators, and then from that point of view, quantum Boltzmann, quantum diffusion, I will slow down and I will go through line by line the equations. I will certainly not be able to cover everything. This is meant to be a longer talk, but some of the technical details maybe we can discuss in the afternoon in the question answer session. So let me start with the very basic things about diffusion in classical mechanics. This was well before the mathematics times, when Brown, who was actually a biologist, who first observed what is nowadays called the Brownian motion. He observed under the microscope a light particle which was suspended in water, that it performed a very erratic motion. So this is the picture that Brown actually has seen in his microscope. Now, it took almost a century before the first physical explanation came. It was actually by Einstein and also independently by Perrin. The picture here is the following, that what Brown has seen was only this big black particle, which was a pollen. But then Einstein's explanation, there were tiny other particles. In that case, it's water molecules, which was not visible in Brown's microscope, which was actually responsible for all these motions. So there are many little invisible, for Brown, invisible particles which keep on kicking this pollen, this big tracer particle. Now, there is also an analogous, even more complicated version of that, which goes towards Boltzmann. I will not going to talk about Boltzmann, I just put this picture in a bigger context. This is a situation when the water particles, water molecules themselves also allowed to collide with each other. And even it can happen that the tracer particle is simply not a bigger particle, it's not a distinguished particle, it's just one of the water molecule which you would like to observe. In that case, all the particles play the same role, which just distinguish one particle which you would like to observe. Now, this picture is, of course, much more complicated because this is a truly many-body interacting model. Everybody interacts with everybody else. In contrast with the previous picture, in Einstein's picture, when the small particles are supposed to be non-interacting, they are so tiny that they, say, never collide with each other, but they do collide with the big particle. So these are two different pictures, and of course, the Boltzmann theory, the Boltzmann situation is the more complicated one. Now, Boltzmann introduced the basic concept, which is the phase space density. This is a function which depends on the phase space. So x is a space variable, position coordinate, v is a velocity, and it also depends on time. And roughly speaking, this tells you the density, or rather the number of particles with a certain at a certain position x with a certain velocity v. So this is a basic object which the Boltzmann equation describes. And here is the basic formula, basic Boltzmann equation, which one can derive in various levels of non-rigorous physics arguments, which is an evolution equation for this density, for this phase space density. So it's a first order differential equation. It starts with a time derivative, then it has a convective spatial derivative, v times gradient x. And this whole thing is equals to a quadratic collision term, which is written down here explicitly. Don't look at the details if you haven't seen that before. It's not that important. The quadratic term simply expresses the usual two-body collision mechanism, when there are two incoming velocities and then there are two outgoing velocities. And this is what this complicated formula describes. So that's the nonlinear Boltzmann equation. And behind that, there's a main assumption, which is called the ansatz of molecular chaos, which says that the colliding particles are statistically independent before the collision. So there are two incoming particles, and they are basically independent, meaning that in their prehistory, they have never collided with each other. Of course, this ansatz is wrong, literally speaking, because there are collisions in the system, but this is typically done, this model is done in the low density situation, when the recollisions usually very rare, are usually very rare, and therefore this nonlinear Boltzmann equation is a good approximation. This is the basic equation for any later kinetic studies. Now, how to prove this thing, that's another story, but this is the physical picture behind that. Now, the key conceptual difficulty behind all these things, and also Einstein's model and so on, is that it's based upon a Hamiltonian dynamics, which is reversible and of course deterministic, but on the other hand, at the end, this describes an irreversible chaotic picture. How comes that a deterministic Hamiltonian dynamics leads to an irreversibility? And in one sentence, the basic answer is that there is a loss of information due to a scale separation, which means that you are not following the same amount of information that is needed for the Hamiltonian dynamics. You integrate out lots of microscopic degrees of freedom, and that loss of information is responsible for the loss of reversibility. Now, if you really want to prove something like that, so what does it mean proving it? It means that you start from the Hamiltonian dynamics, the first principle mathematics. You introduce some scaling limit, you introduce some assumptions, and then at the end of the day, you would like to say that the Hamiltonian dynamics, which is time evolution of the true system, can be modeled in a certain limiting situation by the Boltzmann equation or by the linear or nonlinear Boltzmann equation, some other kind of phenomenological equation. And the key technical difficulty behind these things is twofold. First of all, I already mentioned in context of the molecular chaos, you would like to control the memory effects. Typically, these equations phenomenologically designed in a memoryless situation. So assuming that the incoming particles are independent. So as long as you can control that the recollision is not too strong, recollision effect is not too strong, then you are in good shape, and that's actually even necessary. So this is one important ingredient. And the other one, which is a quantum effect, so far my model was classical, but you can easily quantize it, is the interference, which is a typically quantum situation. I will show more pictures about that, but this is basically interference of different elementary waves. If you have a collision history, then there are various wave packages which undergo different collision histories, and at the end of the day, you have to add them up as a wave, so this is the interference. Now, as I already mentioned, that Einstein's model is non-interacting, it's much simpler than Boltzmann, but nevertheless, the Einstein's model already addresses the key issue, namely how does the diffusion emerge from Hamiltonian dynamics. So I will focus on Einstein's model and even a simpler version of that and forget the interacting model. But later on, especially I think Benjamin will talk about truly interacting quantum mechanics later. So that's a different ballgame. Now we have to add some stochasticity to the model. This makes life easier. And where, on which level you add the stochasticity, that determines a lot about the difficulty of the proof. So the stochasticity you can add in at various points. The easiest would be if you consider stochastic dynamics, which is basically what the random walk is, or you can take the scaling limit of the random walk and you lead to the Wiener process. This means that the dynamics itself stops being Hamiltonian. Your particle is randomly being kicked by fresh randomness. At every moment, God tosses a coin, and then it tells you what your next step will be. So this is not really an interesting situation from our point of view, because a priori, from the very beginning, the Hamiltonian nature is killed. The next level is that when you consider a random Hamiltonian, and this is what we will actually talk about, this is like a Lorentz-Gaussian random scatterers. So random Hamiltonian means that you take, for example, random potential, you put some potential bumps all around in the space. The potential is drawn randomly, but after you have drawn after you declared the potential, the random scatters, then you freeze the situation, you fix it, and then you start running a true Hamiltonian model. So actually the dynamics itself is Hamiltonian, just the potential is random. This will lead to the random Schrodinger operator. And then there are two more models which actually have even less randomness. I'm not going to discuss them, but they are there. You can also consider deterministic Hamiltonian, but with random initial data. That's another way of putting in randomness. This is more like Einstein's model, actually, when you have a heavy particle with a big mass, and then it's immersed into a light ideal gas consisting of point-like light particles which do not interact. And then there is an even harder problem. Of course, less randomness means harder the problem when you consider deterministic Hamiltonian and the random initial data, but only a few degrees of freedom. And this would be, for example, the periodic Lorentz gas. So let me show a picture of this. Where is my picture of these four models? So in a very schematic way, the first picture is the random walk. This is the Wiener situation when you have only one particle, and this one particle performs a straight motion up to a random time point when it decides to switch direction again in a random way. So it tosses a coin and then decides to move in another direction. This is the random walk. Now the next picture is the Lorentz gas. This is what we are going to talk about. This is when you have randomly placed scatterers. These are these red dots. These are given once forever. And then you have one single particle which moves in this environment. The third model is the Einstein's model, when these particles, these light particles themselves are dynamical, but they don't interact. And this is the last model, the periodic Lorentz gas. I'm not going to talk about that at all, and our methods are not good for that. But in this situation, the obstacles are not random, say periodic, and the only randomness is in the initial conditions. So the initial point starts from somewhere with a certain random velocity, and after that everything is deterministic. So this is, in some sense, this is the hardest model. And in all these models, one expects diffusion, and actually diffusion has been proven in all these models for the classical situation. So here's a bigger table. Let me not go through this table. It basically just tells you these four models which are mentioned here. And I also added the fifth one, which is the truly many-body interacting situation. And here I listed the results in classical mechanics, and I put some various references. Maybe I didn't refer to everybody. But you see that in classical mechanics, all these models are actually well understood. And now we will talk about the quantum mechanics, a quantum mechanical situation. And the interesting thing is that this box here. So this is the Lorentz gas, random scatters, but in quantized way. So this will be our main playground. And let me just mention that actually the corresponding Einstein's model can also be treated basically with the same methods. The many-body situation, the quantum nonlinear Boltzmann equation, is a big unsolved problem. Nobody knows how to do that. And actually, as just a curiosity, the periodic Lorentz gas, which used to be the hardest problem in classical mechanics, the senile billiard and so on, in quantum mechanics that becomes simple, that becomes basically trivial, because there is a block wave decomposition, so that basically you can solve almost explicitly. Okay, so now, so let me maybe this page is known to everybody. So this is just a stochastic recapitulation of some stochastic dynamics. So I assume that everybody has seen things like generator of a Markov process. Everybody has seen the Wiener process, whose generator is the Laplacian. And here I also mention another process which comes up in the Boltzmann equation. This is the random jump process, this is exactly the process what this Wiener situation describes. When you have a particle which moves in certain direction, suddenly it changes the velocity randomly. Of course, there's an energy conservation, so the length of the velocity is always the same. The only change is the direction on the surface of the unit sphere. And then if it happens completely randomly with a certain rate of jump, which tells you that what is the rate that in an incoming velocity v goes out in the velocity in the direction u, these are two vectors on the unit sphere. If you consider such a process, then this is the generator here, which describes the evolution of the phase space of the density ftv of such a process. So here you already see the structure of the linear Boltzmann equation, at least one ingredient of that. And then this is basically, let me not go through, this is the derivations, an elementary argument in basic probability theory, how one derives this equation. So we have this random jump process with a given generator. Sometimes you write up the same process with the adjoint. There's a direct question, the dual question. So let me just read off the dual question. It simply says that suppose that the initial condition is distributed by some density f0, initial condition of the velocity on the unit sphere, and then you let it evolve later on according to this process that randomly you choose at every unit time you choose a new direction, and then at later time t the density will be ft when ft solves this equation. It's basically the same equation as before, just you have the adjoint operator. The importance, so this is a typical situation, typical structure of the linear Boltzmann equation. This is only in velocity space. I didn't put in configuration variable yet. And it always has this, such an equation has a structure which means that it has a gain term, the first term, and also a loss term. So there's a certain velocity if you come from direction v and go out to direction u, then you lose a unit mass in direction v and you gain a unit mass in direction u. So this is what this fu minus fv expresses. Now the next elementary slide is about the classical mechanics of a single particle. This I guess also needs basically no explanation. So a cubical Hamiltonian energy functions, velocity squared plus a potential. Here's the Hamilton equation. If potential is zero, then you have free evolution. Now we would like to express the same dynamics in terms of phase space density. So in phase space density, if you have only a single point particle, then phase space density is basically two delta function along the product of two delta function along the trajectory. But formally, this satisfies an equation, which is called the Liouville equation. And this looks like this usual convective derivative term on one side, and on the other side you have the force, the gradient of the u times the gradient of the v. So this is the other ingredient which you keep in mind. And now we put these two dynamics together. So there is a single particle dynamics, which is basically a free evolution, plus it will have this jump process on the unit sphere. And that gives you the linear Boltzmann equation. It's a phenomenological equation, phenomenological combination of the free evolution and this jump process. So it looks like that. If the right hand side were zero, that would be just the free evolution, but it's not zero because there's a jump, and the jump happens locally in space, and then it tells you that the velocity u is switched to velocity v at a certain rate. Okay, so this is a phenomenological derivation of the linear Boltzmann equation. And now we still need to see some diffusion. Eventually, we would like to see want to see some diffusion coming up, but this is not very hard. Simply a long time evolution of this Boltzmann equation is a diffusive equation. So it means that you look at the velocity process, for example, coming from the Boltzmann equation, and you integrate it up to a fairly long time. You put in a scaling parameter epsilon, so you run it up to 1 over epsilon time, and you scale it appropriately. That happens to be the right scaling with the diffusive scaling, which is the square root of epsilon, and then the whole thing as a process in this time converges to the Wiener process. So that's a usual way of getting diffusion from the long time evolution of the Boltzmann equation. There's nothing surprising here.
László, are you claiming that this is true for every sigma, every choice of the of sigma?
I mean, essentially, yes. I mean, of course, I mean, if sigma is completely trivial, so there is no collision at all, then it's not. But if sigma is sort of spread out in every direction, then yes. I mean, there are some degenerate situation if sigma is, if sigma is preserved some subspace, it doesn't allow you diffusion in every direction, and of course then it doesn't look like that. But in a general situation, it's always like that. Okay, now let me come to quantum mechanics. This is also well known. So in quantum mechanics, the kinetic energy is replaced by the Laplacian potential stays. The wave function psi describes the position. Its Fourier transform describes the momentum space density. It's very important to stress that the wave function itself does not carry any physical, any observed or any measurable physical quantity. You always have to take the square of the wave function. You have to take a quadratic form of the wave function. So for example, the psi absolute value square or its Fourier transform square, these are the measurable objects. Now in quantum kinetic theory, one usually uses the Wigner transform, which is a mixture of these two things. So here's the definition. So the Wigner transform is a function which is a function of the phase space x and v, as in the classical situation. It is associated to a wave function, and in some sense it expresses the so-called quantum phase space density of the wave function psi. Here is the former. It's a sort of shifted Fourier transform. It's a quadratic object of psi, and shifted and evaluated at two different points with a shift z, and then you take the Fourier transform in this variable. It has the nice properties that its marginals give you back the position and momentum space density. So if you integrate out the v, the velocity of the Wigner transform, then you get back the position space density and vice versa. And also the other good property is that V is real, like a density. The only slight problem is that this is not positive. Typically, the Wigner transform is not positive, but I didn't put it on the slide. But in many cases, if you smooth it out a little bit, so you take a small scale convolution both in x and v, then you already get a positive object. This is called the Husimi transform, and then then the Wigner transform really behaves like a classical density from many points of view. So this is the basic object because we are trying to describe a Boltzmann equation, later on a diffusive equation. For that, we need a phase space density, so the Wigner transform will play the role of that. Okay, so here is just to have a feeling how this Wigner transform really does what you expect it should do. Here is the semi-classical version of the Liouville equation. So I consider a single one-particle Hamiltonian with a quantum Hamiltonian with a potential. And now the only thing that I do here is I put the semi-classical parameter in it. Here it's denoted by epsilon. Usually more familiar if you write it in macroscopic coordinates, you scale the variables, and the same equation looks like that. And then this is probably what you are more familiar with. Epsilon is what is usually called h in semi-classical theory. But now I rewrite it in this other coordinate, doesn't really matter. So these are the two things. And now, if you take the corresponding Wigner transform of the solution, and then you rescale it appropriately. What does it mean, rescaling? The picture here behind semi-classic, the picture is always like that you have a potential which lives on a large scale. This is indicated by this epsilon scaling there. And large means compared to the wavelength. So the wave function is like a wave, you know how it looks like a wave, with a certain wavelength, whose size is much smaller than the typical variation scale of the potential. This is a typical semi-classical situation, and in that case, the true quantum evolution can be described by by the limiting version of the Liouville equation. For that, you have to rescale the Wigner transform in the macroscopic coordinates. So this is how you do it. And then you take the epsilon goes to 0 limit. The limit exists, and the limiting object satisfies the Liouville equation. It looks exactly as the equation before. So quantum mechanics, if you wish, has disappeared, and the equation exactly looks like as before. But notice that there is a limiting procedure behind that. So you have to take epsilon go to 0, and also you have to take the weak limit. It's very important that the weak limit is taken, which means that lots of fine details are lost. The Wigner transform still contains the full information about the wave function, but once you take its weak limit, then lots of fine details described, including in the wave function, is lost, and the only thing which is left over is some global profile which the classical Liouville equation can describe. Okay, so now eventually I come to the random Schrodinger equation, which is, I guess, everybody knows that, so I put in the convention. The most important thing, I would like to put in a small coupling parameter in front of the potential, because I will play with that. It will be a weak coupling limit situation. Otherwise, it's the usual Anderson model, Laplacian plus random potential. Now, there is a little difference between whether you do it in discrete or continuum. In discrete situation, it's easier to describe a random field because then you just have a random potential denoted by Vx at every point x on the lattice ZD. And for simplicity, the simplest case, just assume that these are IID, independent, identical distributed random variables with a certain normalization. If you want to do it on RD, then it's a little bit more complicated. Let me not go through it in details. This is basically involves a Poisson process, a random point process, X alpha scattered around in the space, a bump function, which is some kind of profile around each particle, around each of this Poisson process. And additionally, to make it more random, you can also put a coupling constant in front of every bump, which is an independent randomness V alpha. But actually, in my discussion, mostly I will talk about the ZD because it's easier. That's the easier situation to generate the randomness. Now, also the kinetic energy, there's a difference because in continuum, it's the dispersion relation, which is the Fourier transform of the Laplacian is p squared. And ZD, it's a little bit more complicated. Now, here is, of course, the main open question, is the situation when you have you are at least 3 or higher dimension, and the coupling here is relatively weak. In that case, you expect delocalization. This is called physics in the extended states regime, and that's the big open question to prove it. So here's a picture intuitively. It also shows two different scenarios to weaken the randomness. You see, I mean, in all these models, it's important that the randomness, the random potential is not terribly strong. It should not be too weak to get something uninteresting, but it should not be too strong in order that we can still do something. And there are actually two ways to weaken the random potential. One of them is called the low density, which means that you have few bumps all are scattered around randomly in the space. So imagine that you have Poisson point process with a certain low density, and then around each point, you just put a bump potential around that. This is one picture, and the other picture, which actually we are going to discuss, is the weak coupling situation, when you have random potentials everywhere with a unit density, but their size is small. This is this lambda, and this will be actually square root of epsilon later on. So these are the two different situations, but the most important thing, let me emphasize that the wave function, a quantum wave, has a wavelength which is comparable to the potential. So which is comparable to the spacing, the size of the support of the potential. The wavelength here and the potential live on the same scale. This is very, very different from the semi-classical picture. In the semi-classical picture, the potential lives on a bigger scale, and therefore it's a much easier thing. There's a clear scale separation. Here you don't have a scale separation. The different wavelengths, small wavelengths, very actively interact with the different small wavelengths of the potential. This is true in both situations, both the low density and the weak coupling situation. Now here is the phase diagram for the Anderson model. I guess everybody has seen it, so maybe let me not spend much time on it. So this is just the diagram which shows what is proven and what is open. So here you see in the vertical axis, you see the coupling constant, lambda equals 0 corresponds to the free Laplacian, and then the horizontal axis is the energy. So when lambda equals 0, then you have it's in ZD, so the Laplacian is minus 2D, 2D. If you turn on the randomness, then the spectrum gets broader. These are these black lines. This is not very surprising. But then the question is, where do you see AC spectrum, absolutely continuous spectrum, and where do you see point spectrum? And this is the conjectured line. There is a phase transition between the two regimes. What is expected is that near that inside the spectrum, away from the edges and not too high and with not too big impurity, coupling constant, you have AC spectrum. This is the unknown regime. What is known is that the pure point spectrum at very high disorder and also near the spectral edges, these are proven. So these are the famous Friedrich Spencer, Eisenman-Molchanov localization proofs. And the regime in between, this is completely unknown. Now we will work in this intermediate regime, in this regime in the middle, but we will do it in a scaling limit. So let me formulate our result first in an informal way, and then I will show it a bit more formal way. So the main question is that suppose we're in the delocalized regime. Again, we don't know it yet mathematically that it exists, but suppose that we are there. The question is how fast the state delocalizes. So start with an initial condition, maybe when the initial condition is localized, let this random Schrodinger operator with weak randomness act on it and see how the wave spreads. This is a basic question. And the quantum Brownian motion conjecture says, which has strengthened version, more quantitative version, more precise version of the extended states conjecture, so it's even harder than the extended states conjecture. It says that for a fixed lambda, small but fixed lambda, and dimension at least 3, the location of the electron is governed by the heat equation. So this means that if you take the density of the electron, which is expressed by the absolute value of the wave function, if you take the derivative of that, then in some sense, this is a very, very vague statement. In some sense, this satisfies the heat equation. So the time derivative will be the same as the Laplacian, the same thing, which also means that the mean square displacement, which is just the expected value of x squared weighted against the wave function square, that the mean square displacement is linear in time. So the x squared t scales with t for large time. And also you can ask more precise descriptions. You can ask 2-point functions. You can ask the correlation between the wave at around a certain point x at time t, and correlation together with the same wave at a later time at another point. And these are all supposed to be described by the correlation functions of the Brownian motional Wiener process. Now so this is the dream, and this is very, very hard to prove. Now what our main result informally says that this conjecture, this diffusion, holds up to a certain time scale, and the time scale is lambda minus 2 minus kappa. Kappa here is a positive number, a small positive number, say 1 over 100. This is a technical thing. The important thing is that this kappa is positive. So we will see in a moment why the lambda minus 2 is a natural scaling. Up to lambda minus 2, nothing happens. At lambda minus 2, the Boltzmann equation emerges. And if you run it for an even longer time with an additional factor, lambda minus kappa, then you see the diffusion emerging. So here is this very crude calculation, which says that the rate of collision with a weakly coupled potential is lambda square. So that means that if you run it up to time t, and the number of collisions, number of typical collisions is of order m equal lambda squared times t. So as long as the time is bigger than lambda minus 2, so a factor by an additional factor lambda minus kappa, then you have the number of collisions goes to infinity. lambda is always a small parameter, it will go to 0 eventually. So this is why this scaling is important, because that's why this time scale is important, because on that time scale you start detecting the diffusion. Diffusion needs, of course, many collisions. If you have only 1 or 2 collisions, you don't see diffusion yet. So you have to go up at least to the time scale when the number of collisions goes to infinity. And that's what we actually do. So this is just, the next slide is just a short back of the envelope calculation to argue that the rate of collision is real lambda square. This is just a basic scattering theory. So if you take a single compactly supported bump function scale with lambda, and then you take the Schrodinger equation Laplacian plus this small bump potential, and then you try to see that if you have an incoming wave evolving according to this Hamiltonian, then how much part of this wave goes through according to the free evolution, how much part of the wave is scattered. And a little calculation shows that the scattering part of the wave is a 4-well lambda square. So this tells you that the large part of the wave function and the 1 minus lambda square part of the wave function is unaffected by the collision. This goes through as if the potential bump were not there, and a small part of the wave function gets scattered. So this justifies, back of the envelope calculation justify this lambda square wave. Now here you see this, basically I told you already before, but this shows you again the scaling. So if you are in the kinetic regime, that means that you take an epsilon, which is lambda square, so you rescale space and time with the factor lambda square. This is because the collision rate is lambda square. So up to time, collision rate is lambda square. So you have to go up to time lambda minus 2 at least to see a few collisions. If you don't go up, if you go up to time less than lambda square, you don't see anything, and it's a free evolution. So that's justifies the kinetic scaling. And now if you go with an additional factor, you take a time which is the lambda square, lambda minus 2 scale times an additional big factor, lambda minus kappa factor, and you rescale the space with an additional factor, lambda minus kappa over 2. So the additional factor is in space is the additional factor, square root of the additional factor in time. That's the diffusive scaling. Under this scaling, you expect to see the heat equation. And that's eventually what we prove. So now let me come to the explicit theorems. So let me just recall the phase space density. We already discussed that. That's the right object to write up from a wave function psi. If you want to see a kinetic equation, you rescale it because you go to the macroscopic coordinates. Now, if you go up to time scale, so read it from here. You take a wave function psi, which evolves up to a time scale of order 1 over epsilon. Epsilon is lambda square in the kinetic situation. Then you take you evolve the true Schrodinger evolution. You take its Wigner transform, and then you take the expectation with respect to the randomness. This you can remove later on. And then this Wigner transform, which is a function, it's a real valued function on the phase space. It converges, as epsilon goes to 0, converges to an epsilon independent function on the phase space, which satisfies the linear Boltzmann equation. And with a collision kernel, which is given by the microscopic data of the whole problem. So in the ZD case, the easier case, the collision kernel is just a delta function on the energy surface. E is the energy, the dispersion relation. It just expresses the fact that the energy of the incoming wave and the outgoing wave are the same. And in the continuum situation, it's modulated by the Fourier transform, the bump function. Don't worry about that. The important thing is that the Boltzmann equation emerged. Boltzmann equation is, of course, a non-reversible equation. It emerged from a reversible dynamics, but at the price of taking the weak limit here, a scaling limit and a weak limit, which of course means that lots of details are forgotten. So here's a schematic picture what this does. So you start with an initial condition psi 0. You can do two things with that. Either you let it evolve by the honest Schrodinger evolution. That's what you really would like to do, but that's a complicated thing. Or what you can do is that you take the scaling limit and the Wigner transform of that to translate it into a phase space density. And then you take the Boltzmann semi-group, the evolution of the Boltzmann equation, which is a simpler object, let it evolve there. This is one thing that you can do, or you can let the quantum mechanics evolve the wave function by quantum mechanics, and after the quantum evolution, take the scaling limit. And then what the theorem tells you that this diagram is commutative, so you can mimic the quantum evolution by the Boltzmann evolution. Okay, it's very important. Let me emphasize, keep on emphasizing that the weak limit means that only macroscopic observables can be controlled. So you can also translate the problem in such a way that you take the Wigner transform, you test it against an arbitrary observable, but this arbitrary observable has to live on the large scale. So the fine details of the wave is lost. The wavelengths and the interferences are lost. The only place where quantum feature is retained is in the collision kernel, the Boltzmann equation. And here's the result for the diffusion. I mean, I guess by now you can guess how the result would look like. So it says the following: you take this scaling as we discussed. So you take the additional effect, you run it up to time lambda minus 2 minus kappa. You scale the space accordingly, and then you again take the time evolution of the wave function. You take its Wigner transform. Now, an additional, you do one more thing, which we didn't do in the Boltzmann situation, namely you also integrate out the velocity. The Boltzmann equation can keep track of both position and velocity. Let me go back if I can for a minute. So the Boltzmann equation on x and v on the phase space. But the diffusion cannot keep track of the velocity. The Brownian motion has no velocity. So once when you describe a diffusion, and you don't expect that the velocity can be detected, can be kept track of. So actually you have to integrate out the velocity as well. And then the corresponding function, what is left out of this procedure, it depends on time, it depends on space, and it also depends on the energy. That's because the process process works independently on different energy shells. There is no thermalization in the situation, and energy is still conserved. So the whole process works for a fixed energy. And for that function, which now depends only on space and time, plus this energy parameter, the heat equation holds with a certain diffusion coefficient, which is actually a matrix, a diffusion matrix, which depends only on the energy. And this can be computed by a formula like that, which involves the dispersion relation. It's actually the gradient of the dispersion relation evaluated at taking the average of that on the energy shell. So this is the final result, the quantum diffusion. Let me emphasize that this we can do for a certain, up to a certain kappa, and the kappa is a small number, it's 1/100. Although the whole thing is expected to hold for any kappa, basically for infinite kappa up to infinite time, for d equals 3, but it's not expected to hold for d equals 2. Our theorem works also for d equal to, I mean, our paper actually just proved it for d bigger equal than 3, but that's technical. One could do it for d equal 2 as well. But what is important is that still you don't expect the same thing happening for d equal 2 for arbitrary long time, because it's of course not unproven, but one expects localization exponentially large time scale for d equal 2. So let me just sort of finish. I think my time is slowly up, but let me just finish the situation with this the schematic picture. So what we do is that, maybe read it from the right side. So what we really study is a Schrodinger evolution. The Schrodinger evolution means that you have obstacles. Here's just one single big obstacle. You have an incoming wave. The wavelength is the same, is comparable with the size of the obstacle, and you have a scattering process. Of course, I mean, here I just indicated one scattering process. Most of the wave goes through. This you don't see in this picture. I just draw the scattered wave. This is what happens on the microscopic scale. Now, if you zoom it out on the kinetic scale, then you suddenly see many, many of these obstacles, but still not too many. And on that scale, the typical wave function undergoes finitely many collisions. Lambda minus 2 is the time scale, the mean free path is lambda minus 2, and you run it up to a time scale under which you feel finitely many collisions. This is a Boltzmann equation. And then the heat equation, diffusion, is yet another zooming out this picture, where now this Boltzmann picture, which is really a random walk, like a random walk picture, then you take the long time limit of the random walk, which gives you the heat equation. Now, what is very important here is that what one really has to do, one has to take the limit immediately, the big limit down here. So you have to start from Schrodinger evolution, and you have to follow the Schrodinger evolution honestly up to the longest time scale, up to the time scale you are interested in the problem. You cannot do it in 2 steps. I mean, it would be tempting to say that first you prove the Boltzmann equation, one limit, quantum kinetic limit, and then going from Boltzmann equation and go to the heat equation. This is the second step, is actually trivial. This is what I started today. But this would be cheating, because what could happen is that in this first limit, you ignore this limit, of course, tells you that lots of interferences are neglected. But then it might happen that quantum interferences, which are negligible on the lambda minus 2 scale, actually do come back if you run it for a longer time scale. So you're not allowed to do it in 2 steps. You have to do it in 1 step, and it's not just a mathematical problem. Actually, this is what does happen in 2 dimensions. In 2 dimensions, all these pictures are still correct, but if you run it for a very, very long time, then eventually the quantum mechanics starts building up correlations, which stops the diffusion, although you don't see that neither from the Boltzmann scale nor from the second level, from Boltzmann to heat equation. So let me just indicate why this is why the problem is really difficult, or I guess you have some feeling about the situation from other studies when you look at a multi-scattering wave process. So here is again a very schematic picture. You have many bumps in your configuration space. You have an incoming wave. The incoming wave just indicated by the level sets of the wave. Now the incoming wave undergoes a collision. Then it generates basically spherical waves in every direction. Then it goes on, but of course it has many possible trajectories. So I just drew 2 possible trajectories, and it undergoes a second collision and so on. And so this very quickly generates a huge set of elementary waves encoded by the various collision histories. But then at the very end of the day, you want to measure the outcome. So you at some point in the phase space, for example, here you put a measurement apparatus, and then you measure the strength of the wave. But of course, at that point, you have to use the superposition principle. You have to add up all these elementary waves. And then that moment, the elementary waves have to be added up by their phases. And that makes it very, very hard, because there are many of these elementary waves, and if you add them up just by their size, naive size, then you are completely off. You have to add them up by their phases, and you have to use the fact that their phases are more or less random, but not exactly random, because there may be that there is some recollision happening along the way. So this is sort of the reason why this is so hard, and there are several other results, related results, which one can do in this way, but maybe let me jump over that. And now let me see, how much time do I have? I don't have a clock here, so probably I don't have much time, I guess. So,
in principle, 1-2 minutes.
1-2 minutes. Yeah. So I think then probably I can just indicate.
You can have questions later too. So.
Yeah, and then because there is a question, so this is actually how I planned that. Now I just presented the main thing, the main ideas, and then maybe in the afternoon I can talk a little bit about steps, about the ideas. So here, let me just finish by an appetizer, or if somebody wants to run away, then you can run away from the afternoon session. So how we actually do that. So it's a big diagrammatic expansion. But it's a rigorous Feynman diagrammatic expansion, which relies on the fact that the evolution is basically a free Laplacian, which is well understood, plus a perturbation, lambda times v. Lambda is small, but the perturbation has to be computed very, very carefully. And in this Feynman diagrammatic expansion, we can basically follow the evolution of these many elementary waves. The Feynman diagrams is a good bookkeeping tool to sort of carry all these big combinatorics which come up when you follow the evolution, the various typical evolution here. And so there's a big Feynman diagrammatic expansion, and then looking at Feynman diagrams, which each of these Feynman diagram expresses one of the elementary waves indicated before. Then you have to do various things with this analysis of this Feynman diagram. The first thing that you have to do is what is called the renormalization of the self-energy. So-called the two-legged subdiagram renormalization. This is one thing that you do. Then you have to identify the main term in this huge Feynman diagrammatic expansion. It turns out that there are many Feynman diagrams, but after renormalization, only one of them is the main term. That's called a ladder graph, because in the Feynman diagrammatic picture, it looks like a ladder. And then the main mathematical proof is that basically proving that the ladder graph is the only relevant thing. Everybody else is small. And this is where usually physicists stop doing rigorous work. Typically, a physics paper in the business arrives at the ladder graph, and then it computes the ladder graph. The computation of the ladder graph is also not very easy, but it's an instructive calculation, and that gives the answer. That gives the Boltzmann equation, later on that gives the diffusive equation. And then there are many other graphs which are small. And a typical physicist says that once the other graphs are small, then you forget them. Yes, that's for each graph it's true. Also, still it requires to prove. It requires a proof. But the main problem with this physics argument, which a physicist usually ignore, that there are many of them. So there is a main term, which is the ladder, and there are many trash. But the number of the terms is much bigger than their size, 1 over their size. So each of them is small. There are many of them, but if you just naively count the naive size of the error graphs and multiply this number by the number of these graphs, then it's infinite, then it's uncontrolled. So one has to do it much better. And this is the main part of our proof, is that one has to introduce a classification of the Feynman graphs. Not every Feynman graph is equally small. There are small ones, there are even smaller ones, there are even smaller ones, and so on. So one introduces a whole grading of Feynman graphs according to their size, and then this is contrasted with a combinatorics, basically showing that yes, there are many Feynman graphs, but only a few of them are small. More of them are even smaller, even more of them are even smaller, and so on. So eventually, most of the Feynman graphs are much smaller than the naive calculation shows. So this requires basically a complete classification of various Feynman graphs, of all the Feynman graphs, and estimate them an appropriate way with a certain way which gains sufficient size of them. So this I can try to explain it a bit later in the afternoon, just maybe 10-15 minutes to explain how this comes. But this is the basic idea. It's a big expansion, and one has to bookkeep everything very carefully. So maybe I should stop here. Maybe that gave you a good introduction. Hopefully it was understandable, and I'm looking forward to question either now or in the afternoon.
So thanks a lot. Yeah, I cannot upload because I have my finger on the space bar. Maybe 1 or 2 short questions, because apparently people want to rest between lectures.
Sure.
For instance.
Should I go?
Okay. Yeah, go. Yeah.
Okay. So thank you for this very fascinating talk. There is something you said. If you start from in a quantum particle, you start from a quantum particle, and you have in sort of some weak disorder limit. You prove that you have quantum Brownian motion in the end, and it tends to the sort of the classical Brownian motion. Mm-hmm. But in 3D, even in 3D, if I'm not mistaken, you can start, if you have localized, you can have localized eigenfunction. If you start from a localized eigenfunction, normally it won't go anywhere. So where is the, how come that you can prove that it will converge to a quantum Brownian motion, whereas normally a localized eigenfunction should remain localized eigenfunction?
Yes, but this I said at the very beginning that this is not in the extended state regime. So, I mean, we are in 3 dimensions, 3 or higher dimensions, and the lambda, the coupling constant is small. So this is supposed to be in the. Let me go back to this picture. So this is the phase diagram of in 3 dimensions, and what we are doing, we are somewhere here. So the lambda is very small. I mean, eventually it goes to 0. And we are near the we are away from the edge. I mean, this I didn't say very carefully, but there are some conditions in the initial wave function which tells me that I'm not in the edge. I'm in the middle. So this is well inside the absolutely continuous part of the spectrum.
Okay.
This will not work in 1 dimension. Our proof is definitely failing in 1 dimension. In 2 dimension, our proof is correct. But that's again not a contradiction, because we follow the evolution only up to a time scale which is much shorter than the typical expected localization scale in 2 dimensions. Remember that in 2 dimensions, the expected localization scale is exponential big in lambda, yes. And we follow it only up to lambda minus 2 minus kappa. So up to that scale, 2 dimension looks perfectly diffusive.
Okay. So until it reaches the scale at which sort of it localizes, it stabilizes on localized, or at least partially on localized eigenfunction.
Yes, I mean, so there is no, for 3 dimension, there is no localized eigenfunction at all. In 2 dimension, this is probably localized, but you don't see it because this localized, in 2 dimension, the localization emerges only after a very, very long time. In the beginning, you don't see it. And we are only at the beginning, if you wish.
Thank you.
László, I had a technical question at the very end of your talk. Maybe you'll say something more about this afternoon, but I just didn't understand what it means for a Feynman diagram to be small. It's small in what sense?
Oh, yeah. So, and this I will say it later. So a Feynman diagram is Feynman graphs have a size. So a Feynman graph. Maybe let me just show one, and then we will discuss it later on. Where is this? Yeah, so maybe you see it in this way. Just look at this formula. So here I take the L2 norm of the wave function. Just look at that guy. Eventually, I will look at the Wigner transform, but just the wave function. And now what the Feynman diagram formalism does is that it expresses this guy as a big sum over something. I will explain it later, but it is basically over graphs, like this is one of the possible graphs. And then every graph has a value. So a Feynman graph is a picture like that. But this picture encodes a value. A value you can compute. Basically, every line has in the Feynman diagram, every line has a value, and then you have to integrate out all these values, and you get a number. So if you wish, then the Feynman diagram is a technical tool to bookkeep a huge expansion, huge perturbation expansion. You do a perturbation expansion, you generate many terms. Each term you can encode by a graph, pictorially by a graph, and this graph has a value which corresponds to the corresponding value in the perturbation expansion. When I talk about the value, the Feynman diagram being small, I really mean that its value is small. So I mean
the value. So it's this canceled thing where there's a lot of oscillation and cancellation.
Yes.
That's small.
Yes. So
I see. I just was imagining the number of vertices or whatever in the diagram, which
yes,
didn't make
no,
sense.
I
see, the
the
value
graph
of
is
it.
a value. So Feynman, every term in Feynman diagrammatic expansion represents one term in the perturbation expansion.
Yeah.
So perturbation expansion, many terms, and the size of that is what I meant here. I will make it a bit more precise on that term. Yes.
So do we decide that no more questions up until the afternoon?
Can I just ask for one thing? I will postpone all the questions to the afternoon, but if you could drop a reference or maybe a reference to a survey to look up even maybe before the afternoon, that would be appreciated.
Yeah, actually, I gave this to your secretary, and I thought that this was mentioned. So actually, I have a lecture notes, which is on the archive, but I thought it
Very
was on
nice.
the web page of the.
Possibly, yeah. I'm sorry if I missed it.
It's a lecture notes on quantum Brownian
Notes on
motion.
quantum Brownian motion.
You
Perfect.
can
Thank
find
you
it
so
on
much.
the archive, and I'm following that basically now. So.
Sounds great. Thank you so much. Yeah, then I'll postpone everything to the afternoon.
Okay, thanks.
László?
Yeah, go ahead.
I have a question, which is that a commutative diagram that you showed comparing Schrodinger flow to Boltzmann flow. How is this? How is your result related to Oscar Lanford's result, in which instead of the Schrodinger flow you had classical mechanics?
Yes, I mean Lanford result actually was mentioned. So Lanford result is also a commutative diagram, if you wish.
Yeah.
So it's about then up here in Lanford there would be a classical dynamics, the true Hamiltonian classical dynamics, and down it would be the nonlinear Boltzmann equation. So the difference, let me go back then, because both Lanford was actually on the picture, just I didn't mention it. So Lanford is down here. This is the many-body interacting Hamiltonian. It's a classical system when every particle can collide with everybody else. This is the situation that I told at the beginning that I don't want to explain in more detail. That's hard.
Oh, okay.
And then what Lanford does is actually also a commutative diagram. It derives from many-body first principle Hamiltonian, a phenomenological equation, which is the nonlinear Boltzmann equation in that case. So Lanford result is of course also the commutative diagram if you want to formulate it in that way, but the setup is very different. That's an interacting situation, which is harder, but also it's a classical situation, which is easier compared to ours.
But in his situation, my memory is that his result is only for very short time.
That's right.
Whereas yours is for a very long time.
That's right, yes. That's right, but that's because it's a many-body system. So typically following many-body systems for a long time is a much harder thing than one-body system. In any case, many-body system is much harder than one-body system, but especially in this situation, it's harder. That's basically due to an addition n factorial. I mean, if you do a perturbation expansion, then many-body dynamics generates an addition n factorial, which usually kills all kinds of standard convergence results. That's a very rough, very high level saying that that's a difference between many-body and one-body dynamics. It has an additional n factorial. And that's the main reason why basically the Lanford proof is as it is, as after 50 years, that nobody can really extend it further.
Okay, thank you.
Okay, so thanks a lot. Sorry, I'm making it shorter. I guess so. Since I've been asked for people to rest, we start again at 15 past.